Hi everyone, I'm Kaave Hosseini, and this paper is about SignRank and discrepancy. This is a joint work with Hamid Hatami and Shahar Lavet. Okay, so let me start with the definition of SignRank. Let's say you have a matrix that's a -1, 1 matrix. The SignRank of this matrix F is defined by going over all real matrices that have the same sign pattern as F, and then you want to look at the rank of those real matrices, and you want to minimize this. So this definition sort of is not very intuitive, how you might find such a real matrix that minimizes this sign rank. And so let me just give you a more instructive definition using an example. Let's say you have this matrix that's -1, 1 patterns. And so these patterns can be realized by the following situation. So you have points for each row and half planes for each column. And for example, the fact that P2 is inside the half plane H3 means that the entry P2 H3 is 1. So if it was outside, it would be -1. So the sign rank of the matrix would be the smallest dimension of a space where I can realize this matrix as this inclusion signs of a bunch of points and half planes. So sign rank of this matrix now here is 3, because even though these are all on the plane and these half plane, these are all two-dimensional, but the problem is these are affine half planes, and in other words, they are three-dimensional linear half planes. So that's why the sign rank is 3. And you cannot really you cannot do smaller than 3. So let's look at another example. Let's look at this matrix of greater than, which is you have 2 inputs, numbers 1 up to n each, and the output is 1 if first input is bigger or equal than the second one, and it's -1 otherwise. So the sign rank of this matrix is 2, because you can realize it in the following way. You can have points on a line, and you have all of these half planes, and it's easy to see that the sign patterns that you get out of these is consistent with the greater than matrix. And again, even though all of these are on the line, but these are affine half planes, so it's two-dimensional. Okay, so, and it's easy to see that actually every sign rank 2 matrix can be, after like removing some duplicate rows and columns and just reordering the rows and columns, you can just get back the greater than matrix. So structure of sign rank 2 matrices is super simple. But surprisingly, it turns out that this already when sign rank becomes 3, the problem becomes very hard. So just given a matrix, deciding if the sign rank is 3 is an NP-hard problem. And it's in fact even harder. It exists R complete, which is, this is a class that's between NP and P space. Okay, so this concept of sign rank is actually, even though it's quite difficult to understand, but it has many fundamental applications in many areas, such as learning theory. It's like one of the main tools to develop PALC learning algorithms is using by computing sign rank. Or in circular lower bounds, you can obtain lower bounds for some circuits. In algebraic geometry, it corresponds to understanding semi-algebraic sets. In discrete maths, it's a classical topic of combinatorial matrix theory that has various applications. And also it's a very important concept in communication complexity, which I'll be describing next. Okay, so the very basic question is, given that we have this concept of SignRank, is that how is SignRank related to all these measures that we have in communication complexity, such as deterministic CC and non-deterministic randomized and so on. So let's go back to this example of greater than matrix, but now think of the inputs to be of this form, numbers between 1 up to the little n. Then again, SignRank is 2, but it's easy to see that this matrix has deterministic communication complexity of maximum possible, which is n. And the next question is, what about randomized communication complexity? How is SignRank related to randomized communication complexity? Well, remember that bounded error randomized communication complexity is defined in this way. So let's say randomized communication complexity with error epsilon is just cost the best randomized protocol with either private or public that achieves error at most epsilon for every input. And it's easy to see that actually the randomized communication complexity of greater than matrix, by which I mean the error that I have, I just want it to be something strictly less than half. So let's just say it's 1/3. This randomized communication complexity is theta of log n. But it turns out that there is a more interesting notion of randomized communication complexity that's quite related to this concept of SignRank. So let me introduce that. So this was introduced by Paturi and Simon, and it's called Unbounded Error Randomized Communication Complexity, which is just randomized error communication complexity, but I allow the epsilon, the error, to be just arbitrarily close to half. So for every input, the error is allowed to be even exponentially close to half. And then you want to look at the best protocol. And it turns out that in this case, this unbounded communication complexity of greater than is just O of 1. So this is also an easy exercise. And it turns out that this is not a chance, that this has a similar situation with SignRank of greater than, which was just 2. It turns out that there is this very interesting result of Paturi and Simon in the same paper that they introduced the concept of unbounded error communication complexity, is that these two concepts are basically the same thing. Unbounded error communication complexity is just log of SignRank plus some constant factor. Okay, so going back to greater than matrix, remember that we know that unbounded error is a constant, and randomized communication complexity is theta of log n. So a very basic question is this the best separation, or is there a matrix that has constant unbounded error, but the randomized communication complexity is little omega of log n? And one of the corollaries of our result is that you can actually have the maximum possible separation. So we just give a matrix that has SignRank 3, which means that unbounded error is also O of 1, but the randomized communication complexity is as big as I guess it's omega of n. Okay, so in order to explain our result, I have to now yet explain another complexity measure that's intermediate between unbounded error and randomized communication complexity, and this is called weakly unbounded error communication complexity that was introduced by Babai, Franco, and Simon. So in weakly unbounded error communication complexity, I allow the error to get close to half. So I look at randomized protocols where the error is allowed to be even half minus delta, where delta could be as small as you want, but I have a penalty of log of 1 over delta. So the cost of the protocol is going to be randomized communication complexity plus this log of 1 over delta. And you can minimize this over all delta between 0 and half. So obviously, this is going to be at least unbounded error randomized communication complexity, and this is at most just bounded error communication complexity. Okay, so now let's look at another interesting example, given now that we have this extra definition. The set disjointness problem. It has unbounded communication complexity log n. Weakly bounded is also around log n, and famously, its randomized communication complexity is omega of n. And so in the same paper by Babai, Frankel, and Simon, they asked this question that if it's possible to separate unbounded error and weakly bounded error communication complexity. And this has been an active line of work. But before explaining the known results, let me introduce a very interesting combinatorial measure that actually corresponds to weakly bounded error communication complexity. So same way that unbounded communication complexity had an interpretation in terms of SignRank, weakly bounded also has a very interesting combinatorial interpretation, that's discrepancy. So what is discrepancy? Let's say, again, you have a function, you have a matrix, but now let's think of the rows indexed by 1 up to n and columns indexed by 1 up to n. And pick a distribution over the inputs, over the entries of the matrix. The discrepancy is by computing the correlation of the matrix with combinatorial rectangles. So I go over all rectangles, and I want this value here is just the bias of this region where the inputs are chosen according to my distribution. But then I have to maximize over all rectangles. And then I have to also minimize it over all distributions. So discrepancy is going to be a number between 0 and 1. It basically just captures the maximum bias that you can get where you look at bias on rectangles. Okay, and very interesting result, a couple of results that we have is that W of F, the weakly bounded error communication complexity, is basically just log of discrepancy, like log of 1 over discrepancy, but you just have like some log n term on the right side. So the lower bound is due to Coral Goldreich, and the upper bound is due to clock. Okay, so let me now mention the known result between separating these two, unbounded and weakly bounded, or equivalently SignRank and discrepancy. So let's say now in this case, let's say our function is on the Boolean cube because we want to just talk about in this way. So there's a very long list of a long list of results. Basically, all of them have the shape of constructing a function that has SignRank around just linear in n, but discrepancy is exponentially small, and the work has been around improving the exponent here. But what we show is that we just give a very simple function that has SignRank 3, as small as it can get, but the discrepancy is as small as it can get, which is right to the minus n. Okay, so now I have to tell you what is our function. So the hard function that we have is the most trivial SignRank 3 function you can think of. So it's just f is just a function on three-dimensional vectors. So it's like three-dimensional vector x, a three-dimensional vector y, and I just look at the sign of inner product of x and y. Equivalently, you can think of x to be the points that we had, and y, you can think of these y's as normal vectors for half planes. So you just want to see if this point belongs to a half plane with the normal vector of y. So in this interpretation, it's easy to, then, as I described earlier, just the SignRank of this matrix is just 3. And what we show is that the discrepancy is roughly 1 over square root n, where n was this. Notice that the discrepancy cannot really be smaller than 1 over poly n. Okay, so now let me just tell you what is the general approach for the proof. So to be more specific, we actually work with a sub-function of this function f that I just described. So the sum function is as follows. I take x to be a two-dimensional vector here, y to be a two-dimensional vector, but then I have one more input, z. Z is just in the range of this inner product. So the range of this inner product is 2n squared. So z is just picked from numbers 1 up to 2n squared. And I define this function f to be on these 3 inputs to be just sine of xy minus z. So basically, I'm just checking if this inner product is bigger than z or not. But now the problem is, well, this is not a matrix anymore. It has 3 variables. So we change this by looking at zx. We give zx to Alice, and we give y to Bob. So the matrix we have is the rows are indexed by zx and the columns are indexed by y. Okay, so now what is it that we're trying to do? I have to tell you the discrepancy of this matrix is small, so I have to define a distribution over the inputs, over the entries of the matrix, so that all rectangles are roughly balanced when normalized. So roughly all large rectangles are balanced. So that means if you pick let's say, so the both letters here correspond to random variables. So if I take my points from the distribution and I want to look at this correlation, it has to be 1 over poly n for all subsets of the rows and subsets of the columns. So the basic question is, okay, so what hard distribution we should choose to show discrepancy is small? Okay, so this is the distribution, or like just a general approach to construct a distribution, a hard distribution. You pick x uniformly randomly, pick y uniformly randomly, but pick z to be just the inner product, but you introduce some error e, where e is chosen independently, but comes from a suitably chosen distribution that I'll describe later. So overall, Alice gets x and z, which means Alice gets x and gets the inner product of xy plus e, and Bob gets y. And showing that the discrepancy of this matrix is very small basically is similar to saying that Alice and Bob, so what is the goal? Alice and Bob want to compute the entry of the matrix, which corresponds to checking if xy, inner product of xy is bigger than z, which is same as asking if this is negative or positive. So all they want to figure out in this game is if the error is positive or negative. And what we show basically is that in order to figure this out, they basically have to just compute the inner product, and then Alice can subtract things and figure out what E is and see if it's positive or negative. Okay, so again, the function f just checks if the inner product is bigger than D, which is the same as if E is negative or at most 0. So I have to now I have to tell you, how do I pick this error E? From what distribution do I pick E? So here's one necessary condition. E should be chosen in a way that it doesn't take very small values or very large values often, because if E was very small, then to compute this, I could just look at very low significant bits of this inner product. And low significant bits of the inner product are easy to compute. They don't need complexity of omega of n. And same is true for very high significant bits of the inner product. So E should not take very small values or very large values. Okay, so the question is, what E should we pick? And one type of error that works is the following. So first you define a random variable k, that's k1 plus k2, where k1 and k2 are just uniform from 0 up to n. And I pick E to be either k or k minus 2n, which is just basically minus k. And I pick these with equal probability. So the histogram of E is going to be something like this. So it's like roughly symmetric around 0, and it doesn't take very small values. And so notice that in this case, E is always positive, and in this case, it's always negative. And these two happen with equal probability. So our function is, the matrix is balanced. So just to recap again, Alice has input x and has this inner product of xy plus this error, and Bob has y. And the goal is to upper bound the discrepancy of this particular distribution. So again, I want to say that all large rectangles are roughly balanced. So these are the rows and these are the columns. And another way of saying the same thing is the probability that the error is at most 0 if I condition on my inputs coming from the rectangle that I fixed, is this going to be roughly half. So it's like half plus minus 1 over poly n. And this should be true for all large rectangles. Okay, so instead of showing this, let's just show some toy goal, which is just upper bounding the discrepancy of the entire matrix. So I just look at AV to be all the rows and all the columns. Well, this has an easy answer. The discrepancy is 0. Just by the definition of my distribution, the probability of E being bigger than 0 is just half. And this exactly corresponds to 1 inputs, or minus 1 inputs, one of them. And the other case corresponds to the other case. So the function is completely balanced with this distribution, which means discrepancy is 0. But there is another answer that's more complicated, and that answer can be generalized to arbitrary rectangles instead of the entire matrix, because right now I cannot really talk about arbitrary rectangles anymore. So now let's just consider this more general, more like detour kind of argument. So the argument is as follows. So remember that the error that we chose was either this k, where k was like sum of two uniformly randomly chosen numbers, or it's k minus 2n. So in this case, it's positive. In this case, e is negative. So now let's just take a typical x, and what we want to show basically is roughly just saying that it's hard to distinguish between these. Typically, like for a typical fixed x, it's hard to distinguish between this random variable, which is the case that e is positive, and this random variable, which is the case that e is negative. So this is the input of Alice in the case that e is positive, and this is the input of Alice in the case that e is negative. And I want to say it's hard to distinguish between these two. Well, in other words, I want to say that the total variations distance between the distribution of this random variable and this one are very close to each other. Like the total variation distance is very small. Or another way of saying the same thing is that if you look at the distribution of this inner product plus k, and you translate this distribution of this by, you translate this random variable by 2n, you shouldn't change the distribution much. So the distribution basically is almost invariant under translation by 2n. And that's what we show. So we have, the main technical lemma is that we show that for a typical x, for typical input of Alice, the distribution of this random variable is roughly invariant if we just have a shift of around theta of n. And then we use this lemma by just taking theta of n as 2n. And the proof is Fourier analytic, and basically, like, it's quite technical, and it involves studying like mixing properties of the inner product function, where the inputs are chosen from arbitrary product sets. And along the way, we have to compute some strong upper bound for some partial exponential sums. Okay, so that's as far as I can tell you about the proof, but now let me just summarize the result. So again, we had a function f that has sign rank 3, and it's very simple. It's the sign of inner product. We show this discrepancy is 1 over poly n. And as a corollary, if you think of the same function as a function on bit strings, this has unbounded error communication complexity of a constant, but weakly bounded error is omega of n. Okay, thank you.